So, this is the circuit theory lecture, and we were discussing hybrid parameters. We were discussing two port parameters, different kinds of two port parameters, right. Two ports are there V 1, I 1, V 2, I 2. Out of these four different voltages and currents, you can choose any two as dependent and the other two as independent, right. Depending on your choice, you have different sets of two port parameters. So, we have names for each of these 4 C 2. So, 6 different combinations, we have names for each of these. In the previous class, we had studied Z parameters and Y parameters, and then we just about started talking about the hybrid parameters, which are H and G, and much later after a few more classes, we are going to, or maybe in the next class or whatever it is, right after some classes, we are going to talk about the other two port parameters. So, total 6, out of which 2 we have already done, 2 are there in front of you, hybrid parameters, and then there are going to be 2 more in future. All right. So, H parameters, which are the dependent ones, which are the independent ones? V 1 and I 2 are dependent, I 1 and V 2 are independent. Okay. How will you remember which is what? For example, it is easy to figure out what the content of what is this one going to be. V 1 V 2 is equal to, what will you call this? Z, because the dimensions of all the 4 parameters are impedance. Okay. Similarly, it is easy to figure out what is the situation if this is I 1 I 2 is equal to something times V 1 V 2. Okay. What is this called? What is this matrix called? Y. Fine, it is very clear what these are. Okay. What is not clear is what do we call V 1 I 2 is equal to what times I 1 V 2, is it H or is it G, right, that is what is not clear. So, what you have to remember always is that it is important for us to talk about a current controlled current source, all right. So, this is what you have to remember, current controlled current source. A current controlled current source is a very important circuit component. If you can make this somehow, then you can make a lot of very interesting circuits, all right. Not VCVS, not VCCS, CCCS. Okay. So, this is super important for circuit theory, not really for circuit theory, for future circuits, this is super important, current controlled current source. Now, if you want a current controlled current source, then at port 1 what should be the input? I 1 or V 1? I 1 should be the input, not V 1, because it is current control. And if it is a current source, what should be the quantity at port 2? I 2, not V 2. Okay. So, which should be dependent, which should be independent? I 1 current controlled. So, I 1 has to be independent I2 has to be dependent. All right. That is how you remember which is H. Okay. And G you do not have to remember. G is not worth remembering, you I mean it is just the opposite of H. G is really H inverse. Okay. So, no need to remember G, all you need to remember is this word current controlled current source CCCS, and CCCS means it is in which parameter set are we talking about? We are talking about the H parameter set. Fine. You have understood why CCCS is H parameter? Current control. So, port 1 has to have a current, okay. Current source. So, port 2 has to be a current, and port 1 the current has to be dependent or independent? Independent, and port 2 the current is dependent. Fine. Okay. What will be the H parameters of an ideal current source? Ideal CCCS. Let us say ideal CCCS of value k. Yeah, how much is H11? 0. How much is H21? K. Very good. And H12? H12. Reverse. So, what do you do with port 1 for H12? What we open circuit port 1. Okay, I have got I1 at port 1. Okay, you guys are blanking out. How will you compute each of these? So, over here V1 I2 is equal to some H matrix times I1 V2. If I want to find out H11, then what will I do? V1 is equal to H11 times I1 plus H12 times V2. How will I do it? I will set up V2 to be equal to 0 and then measure V1, and that will be H11 I1. Okay. So, the experiment is make V2 to be equal to 0, right, push 1 ampere of current. So, make this 0, push 1 ampere of current at I1 and then measure V1, you will get H11. Okay. Measure I2, you will get H21. Similarly, instead of 1 0, I make it 0 and 1, I make I1 equal to 0 and V2 is equal to 1, right. And now what will happen? V1 will be equal to H12 matrix multiplication. Guys, okay, you can't just look at the screen. V1 is equal to H11 I1 plus H12 V2. Okay, now I have made I1 equal to 0, V2 is equal to 1. What happens? V1 is equal to H12, that is it, and I2 is equal to H22. All right, that is how you measure H22. What will you do? You will set up I1 to be equal to 0, means port 1 is open circuit. So, I open circuit port 1 and I apply 1 volt at V 2 and then I measure V 1, I get H 12, I measure I 2, I get H 22. That is the technique. Okay, always to start you need the matrix setup. Okay. If you know the matrix, now you can start, you make it 0 1, make it 1 0, fine. All right. So, it is very important to know the matrix. You have learnt how to memorize the H matrix setup, right. What do you, how do you memorize? By remembering that a current controlled current source is related to H, fine. Nobody wants voltage controlled voltage sources, they all want current controlled current sources. Okay. So, let us continue. So, we were trying to develop this ideal current controlled current source, H parameters. First experiment was short circuit port 2 or open circuit port 2. What do I do? H parameters. I 1 is 1, V 2 is 0. So, what do I do to port 2? Short circuit port 2. So, that is the first experiment, short circuit port 2. All right. Then push I 1 is equal to 1 ampere and measure V 1 and measure I 2. V 1 is going to be 0. So, H 11 is 0, I 2 is going to be k times 1 ampere. So, H 21 is k. Is this okay? Okay. Next experiment. What is the next experiment? Open circuit port 1 and short circuit port 2. Sorry, open circuit port 1 and apply 1 volt at port 2. So, I am going to open circuit this port 1, no current coming in. So, what is I 2? I 2 is 0. So, H 22 is and yeah, what is H 12? What is V 1? Port 1 has been open circuited. What is V 1 going to be? Yeah, that is fine. I am trying to find out what is H 12. Suppose there was some tiny resistance over here. Now, what will V 1 be equal to? Huh? But I 1 is 0, it is open circuit. What is the confusion over here? I have, what is the experiment we are doing? We have applied V 1 over here, some voltage, 1 volt we have applied, and over here we are not connecting anything. All right. So, I am not connecting anything to port 1, I have applied 1 volt at port 2. Okay. So, if this current is I 1, I 1 is automatically equal to 0. We have open circuited to make I 1 equal to 0. This is equal to 0. Okay. If there was some wire resistance over there, something, what is V 1 going to be equal to? This is V 1 for those who have forgotten. Come on, H 1 2. I 1 is 0. What is V 1 going to be? 0. There is some resistance over here. I 1 is 0. What is V 1? 0. Therefore, H 1 2 is equal to fine, and H 2 2, what is I 2? I 2 is k times I 1, I 1 was equal to 0. So, H 2 2 is equal to 0, fine. So, for an ideal current controlled current source, this is the set of parameters 0 0 k 0, okay, where k is the transfer current transfer coefficient. All right, never mind. Let us do an example. Let us do one more example. Yeah, again, what is the setup? We are trying to find out which parameters? H parameters. So, what will you write as dependent? What will you write as independent? V 1 I 2, I 2 is always dependent, I 1 is always independent, fine. Okay. Now, experiment 1, you are going to apply a short circuit at port 2 and you are going to push 1 ampere into port 1, make this as 1 0. This is experiment 1, and experiment 2 will be make this 0 1, right. I 1 V 2 0 1 will be experiment 2, I 1 V 2 1 0 is experiment 1. This is the plan. Okay. So, let us do experiment 1 first. I 1 is 1 ampere, V 2 is 0 volts. So, this is a short circuit. Okay. What is V 1? How much is V 1 now? So, H 1 1 is equal to I 1 is 1 ampere. So, R 1 and R 2 are in parallel with each other. So, H 1 1 is R 1 in parallel with R 2. Okay. H 2 1, I have pushed I 1 of 1 ampere, I get current division. How much current proceeds through R 2? R 1 upon R 1 plus R 2, and then what is I 2? Thank you. Done. Okay. This is experiment 1 is complete. Next we proceed to do experiment 2, and in experiment 2 we are going to remove this short circuit and apply 1 volt over here, and for I 1 we are going to leave it open circuit. So, nothing to be done with I 1, I 1 is equal to 0 in experiment 2. Now, what is going to happen? What is going to be V 1 times 1 volt. So, H 12 is equal to R 1 upon R 1 plus R 2. Fine. And finally, what is I 2? One upon R 1 plus R 2. Is this okay? So, this is the complete matrix. Any observation? Is this called skew symmetric? Yeah, this is not skew symmetric, but anyway, the off diagonal elements are negatives of each other. So, H 12 is equal to minus H 21. This is the observation. Okay. And this will come from Telegon's theorem. You want to prove it? Shall we prove it? That it is always true when the circuit is passive. So, this is H 12 is equal to minus H 21 when the network is passive. Okay. Not otherwise. For example, we just saw in this case when we were doing the current controlled current source, H 12 had nothing to do with H 21, right. H 12 was 0, H 21 was k, all right, and a current controlled current source is not passive. Is it passive? No, it is generating power, all right. So, when you have a passive circuit, it turns out that H 12 is always going to be equal to minus H 21, and you can use this as a sanity check in your exam or in your homework question, wherever it is, wherever this question comes up, calculate H parameters, or you could use it to reduce your workload. Time is running out, what is H 12? What is H 12? Just write it as minus H 21 in case the network is passive. Okay. So, let us prove that. So, we are going to do two experiments, right. In the first experiment, we are going to apply a 1 ampere current source, all right, and we are going to measure the current over here with an ammeter. Am I right? ammeter, not voltmeter, and we are going to measure the voltage over here. This is experiment 1, and in experiment 2, what are you going to do? You are going to apply a voltage at port 2 and what were the two experiments? 1 0 0 1. On here I will just simply measure the voltage and make sure that it is an open circuit. Okay. One is short circuit, the other is open circuit. Okay. So, this short circuit, so to apply Telegan's theorem, I need the network to be the same, the graph of the network to be the same. How do we make the graph of the network the same? Resistance. What resistance? Oh, 0 resistance. Okay. Better still, I am going to use a 0 volt voltage source. Okay. So, over here I am going to use a dummy 0 volt voltage source. All right. And over here I am going to use a dummy 0 ampere current source. Fine. And then we are going to start with Telegan's theorem. Now, whenever you are working with Telegan's theorem, please be careful about the directions. The direction of the current has to align with the direction of the voltage when you make the measurements before you do the dot product. Okay. Be careful with it, because a mess there is going to lead you surely to the wrong answer. Okay. So, experiment 1, let us list out all the voltages and currents. Let us call this experiment A, and experiment B, right. And I am going to list out, first I am going to list out the voltages in experiment A, then the currents in experiment A, then the voltages in experiment B and the currents in experiment B as 4 different lists. All right. So, how many circuit components do we have? We have 2 main circuit elements, and inside the network we have lots of circuit elements. Let us call them n different resistors or impedances. Fine, it is passive. Okay. So, first one, let us start from the left hand side. In experiment A, the current is 1 ampere and the voltage is not really known. Let us call the voltage V1 A. Okay. So, let us call this voltage V1 A, and the current in the same direction. What is the current for that circuit element? Minus 1 ampere. Okay, same direction as the voltage. Be careful, the current has to be the same direction of the as the voltage. Okay. Then the second circuit element in experiment A, the voltage is 0 volt and the current, which way do you want to push the current? Downwards or going into the network? Let us go into the network. Let us call this I to A. Okay. So, let us take the current in the other one. So, let us call the current minus I to A. Okay, because in B it is going to be plus 1 volt. So far so good, because I want to make this consistent with the sign of the voltage. Yeah. No, it is always along that voltage from plus to minus. So, it is minus I to A. No, you could have done that, but we have not. We have put plus on the top, minus at the bottom. You could have done that. That would have been okay. So far so good. Now, let us say there are n different components inside the circuit and let us call them, let us say the currents through them are I 1 A, no I 1 A does not work, I A 1, I A 2 dot 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 I A n, in which case the voltages across them are going to be Z 1 I A 1, Z 2 I A 2 dot 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 Z n I A n, because they all follow Ohm's law. Fine. So, this is experiment A, which is now I have finished, I am done with experiment A. Now, we proceed to experiment B, and in experiment B again I follow the same sequence. V B, sorry, V 1 B is nothing but, yeah, we will write this as V 1 B, and I B in that case is 0, and the current, sorry, the voltage for the next component is 1 volt and the current again is minus I to B. Fine. And let us list out the currents in the internal components. Let us call them I B 1, I B 2 dot 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 I B n. I am sorry, I B 1, I B 2 dot 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 I B n. Then the voltages across those will be Z 1 I B 1, Z 2 I B 2 dot 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 Z n I B n. This is okay. And now, we are ready to apply Telegan's theorem. How do we apply Telegan's theorem? Right, dot product of column 1 with column 4 is equal to dot product of column 2 with column 3 is equal to 0. Fine, that is Telegan's theorem. So, V 1 A times 0, nothing, 0 times minus I 2 B, nothing, Z1 I A1 times I B1 plus Z2 I A2 I B2 plus dot 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 Zn I A n I B n. This is the product of column 1 with column 4, and we are going to equate this to 0, which is also equal to dot product of column 2 with column 3. So, minus V 1 B minus I 2 A plus Z 1 I A 1 I B 1 plus Z 2 I A 2 I B 2 plus dot 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 Z n I A n I B n. Fine. And then what do you see? You see that all these terms cancel out from both sides. Of course, you ignore this 0. We don't need this 0. Okay. They cancel out from both sides, and then finally what do you get? V 1 B is minus I 2 A. What does this tell you? It tells me what was V 1 B? This voltage, and I 2 A is this current. I 2 A was H 21, this was H 21, correct. Port 2 was short circuited, port 1 you applied 1 ampere. So, I 2 A was H 21, okay. And in experiment 2, port 2 you applied 1 volt, port 1 was open circuited. So, V 1 B is equal to H 12, okay. So, what does this tell you? H 12 is equal to minus H 21 in this case. Fine. Any questions? So, when does this hold? When the network is made up of circuit elements that follow Ohm's law. Which elements follow Ohm's law? R, L, C, all kinds of passive circuit elements. Fine. All right. Could it be minus R? Could there be a minus R inside this? Would it still follow Ohm's law? Would it still be okay? Can I have minus 1 ohm inside the network? It is giving power, but it is still following Ohm's law. It is not a passive network, agreed, but it is still following Ohm's law. This cancellation would happen in Telegan's theorem. Why can't you have Telegan can always be applied. No, Telegan's theorem is always applicable. Telegan's theorem you can always apply. So, even if you had some minus 10 ohm resistors inside, even then this would be valid, right. Even though the network was active, right. Here we are declaring network is passive, it will always work, but even if you had minus 5 ohms in the network, even then it would have worked. right, H21 would still be equal to minus H12. Okay. So, it is actually broader than passive. The conclusion is more than passive. All right, this is good. So, H parameters we have more or less studied, G parameters we are not going to bother, all right. It is just a waste of time. G and H are they related to each other? They are inverses of each other, just like Y and Z are also inverses of each other, G and H are also going to be inverses of each other. Okay, so, we are not going to spend extra time studying G. If you know one set of parameters, can you find out another set of parameters? For example, if you know the Z parameters, if you know V 1 V 2 is equal to Z 1 1 I 1 plus Z 1 2 I 2, V 2 is equal to Z 2 1 I 1 plus Z 2 2 I 2. Can you find out the H parameters? Yes. How? By rearranging the equation, right. For H parameters, what do you need to know? You want to find out V 1 and I 2 in terms of I 1 and V 2. So, you simply have to reorganize the equations to find out V 1 and I 2 in terms of I 1 and V 2 from this. You will be able to find, right, just some simultaneous substitution, use substitution, whatever works, right. You should be able to find V 1 and I 2 in terms of I 1 and V 2. Okay. So, given any set of 2 port parameters, you can always do rearrangement, you can always do substitution to figure out other sets, all other sets of 2 port parameters. So, any one set of 2 port parameters is sufficient, you should be able to compute all others. Fine, done, great. Now, we are going to play with these 2 port parameters a little bit, and our first play is going to be as follows. So, I have two networks, network A and network B. So, we are going to call this V 1 A, V 2 A and V 1 B and V 2 B. Fine. And similarly, this current is going to be I 1 A, I 2 A, this is going to be I 1 B, I 2 B. All right. And now, we are going to interconnect these. So, our first interconnection is going to be as follows. We are going to hook up in this fashion, and from outside I am going to call this overall voltage as V 1 this overall voltage as V 2 and this overall current as I 1 and this overall current as I 2. This is the plan. And the question is, if I somehow have been told what are the 2 port parameters of network A and network B, then can you find out the 2 port parameters of the combination? Okay, this is the question. So, network A, network B, we know the 2 port parameters. If you know one set, you can find out all other sets, right. So, some set is given, you can find out whichever set is relevant. The question is, what are the 2 port parameters of the whole thing V 1, I 1, V 2, I 2. All right. Whole thing means this network, this big network. Okay. So, let us make a few observations. What is the relationship between V 1, V 1 A and V 1 B? They are all equal. Okay, equality. What is the relationship between V 2, V 2 A and V 2 B? These are also equal to each other. All right. What is the relationship between I 1, I 1 A and I 1 B? I 1 is equal to KCL. And what is the relationship between I 2, I 2 A and I 2 B? KCL. I 2 is equal to I 2 A plus I 2 B. Is this okay? So, therefore, I 1 I 2 is equal to I 1 A I 2 A plus I 1 B I 2 B. This is okay? And I 1 A I 2 A is related to V 1 A V 2 A through some relationship Z. Y, admittance. So, let us say we know the y parameters of network A. I 1 A I 2 A is nothing but y A times V 1 A V 2 A, all right, and I 1 B I 2 B is nothing but y B times V 1 B V 2 B. But both of these V 1 A V 2 A and V 1 B V 2 B and V 1 and V 2, they are all equal to each other. So, I know do not need this A B business, I can delete the A's and B's, right, they are all the same, and in fact, I can take it common. which is going to give me fine. So, this is what I have I 1 I 2 is nothing but something times V 1 V 2, and therefore, the y parameters of the overall network is equal to the sum of the individual y parameters. Is this okay? So, if you hook it up, if you hook up your circuit like this, right, the y parameters of the sub circuits are going to add up to give you y parameters of the overall circuit. What kind of hooking up is this? Parallel shunt. So, port 1, the two port 1s are in shunt with each other, the two port 2s are also in shunt with each other, right. So, this kind of hooking up, this name, the name of this game is called shunt shunt, all right, shunt in port 1, shunt in port 2. So, both sides they are in shunt, and therefore, you are going to use y parameters, and the y parameters are simply going to add with each other, right. Just like when two resistors are in shunt, you use conductance and the conductances add. Just like that, when the two port networks are in shunt, then you are going to use y parameters, the admittance parameters, and the admittance parameters are going to add with each other. Is this okay? How are the potentials equal? With the wiring, there are wires. You can see the wires or no? The red wires. V 1 is between here and here, right, but this point is also this point. So, V 1 A is nothing but V 1, and similarly V 2 and V 2 A are the same, and similarly V 1 B and V 1 are the same, and V 2 and V 2 B are also the same. All right, this is called shunt topology, shunt setup, right, and you are going to use y parameters. If you have gone with me with shunt, then what else can we do? Louder? Series. Okay. That is the next thing that we are going to do, right. And what are we going to do after that? Shunt series and series shunt, great, right. All these are the four possibilities, all right, four different possibilities. So, the same setup, just that port 1 and port 2 in series they are going to be in series with each other. All right. So, this is the series topology, and here what is the relationship between V 1, V 1 A and V 1 B? V 1 is equal to V 1 A plus V 1 B, and here what is the relationship between V 2, V 2 A and V 2 B? V 2 is equal to V 2 A plus V 2 B, and then what is the relationship between I 1, I 1 A and I 1 B? They are not necessarily equal. I 1 is certainly equal to I 1 A, that much is certain. I 1 is equal to I 1 A, but I 1 A and I 1 B need not be equal, right. Let us put an equal to over here with a question mark. These need not be equal. In the general case, this need not be true. Even then, it can go to the other port also. So, all that you are saying over here is I 1 A plus I 2 A is equal to I 1 B plus I 2 B. That is the only conclusion you can make, right. You can't make the conclusion that I 1 A is equal to I 2 A, but let us put a qualified equal to over there. And similarly, what is the relationship between I 2, I 2 A and I 2 B? I 2 is certainly equal to I 2 A, right, but we do not know if it is really equal to I 2 B. So, we put an equal to with a question mark. Let us move forward with the assumption that it is equal, but with the knowledge that it might not be equal, it depends. So, it could be equal. I can, for example, create 2 port networks where they are equal, but if my 2 port network is horrible, then these need not be true. So, in the general case this is not true, in some cases they might be true. Yeah. So, we are going to go ahead and solve it for when they are true. So, when they are true, right, when this is this and this are, there is no question mark, they are true, we are working with such a situation. So, in such a case what is going to happen? My V 1 V 2 will be equal to V 1 A V 2 A plus V 1 B V 2 B, right, and V 1 A V 2 A is nothing but Z A times I 1 A I 2 A, and V 1 B V 2 B is nothing but Z B times I 1 B I 2 B, and in case these two are equal to each other and they are equal to I 1 I 2, in such a case I get Z A plus Z B times I 1 I 2. Fine. Let us just look at an example. Suppose these are your two port networks. What are the Z parameters? We solved this T network, remember, in the previous class. You have to open circuit port each of the ports one by one, push 1 ampere and measure the voltages. So, open circuit port 2, push 1 ampere into port 1, what do you get? R 1 plus R 3 is V 1 and V 2 is R 3. Experiment finished. Now, I open circuit port 1, I push 1 ampere into port 2. What voltage do I get? V 1 is R 3 times 1 ampere and V 2 is R 2 plus R 3 times 1 ampere. Fine. Let us try the second network. Is the second network any different? Nothing much. It is pretty much the same, okay, just drawn upside down. All right. So, what will be the Z parameters for the second network? Okay, this is what I have. Fine. Now, what we are going to do is we are going to go ahead and join them up, series configuration. All right. Now, you have a mess of wires which are doing nothing, right. You have current entering this way and current entering this way, I 1, I 2, right. All of this current either this way or this way, it does not really matter which way they take, because the two wires are the same wire, right. So, what is the current going to be in this wire? I 1 plus I 2, this joined wire is also going to be I 1 plus I 2, fine. And you could split it up in any way you want, and you can always say that I 1 A is equal to I 1 B and I 2 A is equal to I 2 B. It does not really make a difference to you, fine. So, this is going to be valid in such a case, all right. And what will I have as my net 2 port parameters? Net 2 port parameters will be the sum of these two, and I should get R 1 plus R 3 plus R 4 plus R 5, and over here R 2 plus R 3 plus R 4 plus R 6, and here R 3 plus R 4, and here R 3 plus R 4. This should be my net Z parameters. You want to double check that this is indeed the case, or you are satisfied? It is okay. It will always split in I 1 and I 2, because that is imposed by what you have done outside. The KCL is outside. you do the KCL across this voltage source or whatever is here, it will automatically satisfy. So, the outside component imposes that KCL. So, you do not have to worry about it. Whatever is outside the network, that imposes the final KCL to ensure that current going into port 1 comes out from port 1, current going into port 2 comes out of port 2. Okay. Is this okay? All right. We have done shunt, shunt, we have done series, series. Next will be series shunt. The KCL outside will give you. You will have some circuit element outside, maybe a resistor, maybe a capacitor, maybe current source, maybe inductor. Right, maybe a combination of elements. You have something over here, right. That is already satisfied. That is already satisfied by virtue of the connections. V 1 is always equal to V 1 A plus V 1 B. Okay. So, next we are doing the series shunt topology, and series shunt means port 1 they are in series and port 2 they are in shunt. Very good. And which 2 port parameter do you want to use? H. Very good. We are going to use the H parameters in this case. Okay. So, what is the relationship between V 1, V 1 A and V 1 B? Sum. V 1 is equal to V 1 A plus V 1 B. Great. And that is because we have placed port 1 in series and port 2 is in shunt. So, therefore, you expect I 2 to be equal to I 2 A plus I 2 B, which is coming from a KCL at this point, at this node. All right. Next, what is the relationship between I 1 A, I 1 B and I 1? So, we know for a fact I 1 is equal to I 1 A, and then we do not really know whether it is going to be equal to I 1 B. Okay. Hopefully, it is, in which case we can apply the H parameters. If it is not, then we can't apply. And lastly, V1 sorry V2, V2A and V2B, what is the relationship? They are equal, they are truly equal to each other. V2 is equal to V2A is equal to V2B. Done. So, there is a question mark, right. You have to be careful whether the question mark is correct or not, right, but otherwise everything is fine. So, what can you say? V1 I2 is equal to V1A I2A plus V1B I2B, right, and V1A I2A is equal to H A times I1A V2B. And V1B I2B is HB times I1B V2B. Fine. And V2B and I am sorry, this has to be A. V2A and V2B are certainly equal to each other. So, they are equal to V2. I1A and I1B need not be equal to each other, but let us assume they are, in which case this whole thing becomes equal to HA plus HB times I1 V2. Fine. Any questions? So, for example, this one we found the H parameters. Right, just now we had found the H parameters for this network little while back. Where? Right here. Oh, we found the other way around. Never mind. Okay. Suppose you have a network, this one, and suppose you have another network and you do this shunt series at port 1 and shunt at port 2. Is there any guarantee that I1A is going to be equal to I2 sorry I1A is equal to I1B. So, this is the question mark, right. Is there any guarantee? I1A is this current, sorry, I1A is this current and I1B is this current. Are they necessarily equal? No. Okay? No, there is no reason why they have to be equal, in which case you can't do this. All right, this is not an example. So, you have to go case by case, you really have to check this. Without checking this, you will not be able to. I mean, all this is very nice in theory, right, series shunt, right. But whenever you have series, you have a slight problem, you do have to double check before you can make a judgment whether it works or not. Okay. For example, in the previous example, the series did happen, right. In this example, they do not happen. How about here? How about here? Will it work here? Yes, yes, it will work here, right, because you will be able to do it over here. Okay. So, some current comes out, right. What these currents are, we do not really know, right, but I 1 a plus I 2 a comes out over here. Now, which part goes which way, you do not really know. Do you know? No, we can't really make out which part goes which way. Fine. So, it is okay in some situations it is okay, H can be added, in some other situations they can't be added. How about here? Is I 1 a equal to I 2 a? Guaranteed, right. In this case you can cleanly add H parameters, right. This is a better example. Fine. Huh? There is no other way. It is the same current, no? All right. So, in some cases you can do it, in some other cases you can't do it. Be careful whatever you are doing. That is the net moral of the story. G parameters will be similar, but shunt series as opposed to series shunt. And once again, whenever there is series involved, be careful as to what exactly you are doing, right. Do not do it without thinking. All right. So, we have series, shunt, these are the 4 different topologies. The 4 different topologies go with 4 different sets of 2 port parameters. So, whenever shunt, you are going to use y, whenever series, you are going to use z, whenever series shunt, you are going to use h, whenever shunt series, you see shunt series, you are going to use g parameters. All right, this is the overall plan. Okay. Now, with this we are going to move on to, we are still not going to discuss the last two port parameter sets, we will do it really, we have more things to do before that. We are going to discuss 3 important metrics of a circuit, of a circuit made with a 2 port network. So, typically we are going to use a 2 port network, you will buy a 2 port network from, let us say, the shop, and you are going to use it in the lab, right. But to use it, you are going to apply a voltage source or a power source at port 1, and you are going to apply a load at port 2. Of course, you could reverse the ports, but that is okay. We are going to name the ports according to this. And here the statement is, the problem statement is that we already know the 2 port parameters of the network that you have purchased. You also have agreed with me that if you have one set of 2, if the shopkeeper tells you any one set of 2 port parameters, you can always rearrange and substitute and do all of that to figure out all other possible sets of 2 port parameters, right, using a calculator, whatever it is, you can do it. Fine. That is, so all 2 port parameters of this network are known. Fine. Let us assume we know one of those. Which one? Which is your favorite? Z is everyone's favorite. Okay. So, let us say that V 1 is equal to Z 11 I 1 plus Z 12 I 2, and V 2 is equal to Z 21 I 1 plus Z 22 I 2. This is all known. Now, we have 3 very important metrics of this circuit. The 3 metrics are driving point impedance looking into the circuit, the second is driving point impedance looking back. So, this one is going to be called input impedance, the second one is going to be called output impedance, and the third one is the transfer function. So, I applied V s, what is V L? Right. These are the 3 important metrics of the circuit. So, let us start with Z in. Before you can start with Z in, is there a relationship between I 2 and V 2? What is the relationship? V 2 is equal to minus I 2 Z L. V 2 is equal to minus I 2 Z L. All right. and now you can quickly transpose this and figure out what is V 1 by I 1. Z in is equal to V 1 by I 1, no? Z in is V 1 by I 1. Okay. So, V 2 is gone from the system. So, I have V 1 is equal to Z 1 1 I 1 plus Z 1 2 I 2, but I 2 is equal to minus I 2 times Z 2 2 plus Z L is equal to minus Z 2 1 I 1. Right, I have rearranged the second equation, which tells me that I 2 is minus Z 2 1 I 1 divided by Z 2 2 plus Z L. Fine. I have rearranged the second equation and then substitute it into the first, you will get V 1 is equal to Z 1 1 I 1 minus Z 1 2 Z 2 1 by Z 2 2 plus Z L into I 1. And finally, the input impedance is this result. Okay. I think we have to stop over here, pressure is building up outside. Let us stop, we will do it once again, we will run through this once again in the next class, and we will do all the 3 different metrics before we proceed to the next set of 2 port networks. Thank you.